So we're looking at the same basic setup as the last time, that we're making a graph with n nodes, and again, we're going to assume n is some power of 2. If it's just a single node, we just return that node. Otherwise, we recursively generate the two subgraphs. But now what we're going to do is choose half of the nodes from G1 and half of the nodes that are in G2 and connect all pairs. So for all I1 in S1 and all I2 in S2, we're going to link I1 and I2 together. So we have some graph G1, we have some graph G2. We choose half of the nodes at random to be called S1. We choose half of the nodes at random in this graph to be S2. And then we connect up all pairs so that every single node up here is connected to every single node up here. It gets very densely connected here, but kind of much looser elsewhere. So how many nodes are in that graph? Well, we're going to do another recurrence relation. Once again, a graph with one node has 0 edges. A graph with n nodes has however many edges are in two subgraphs, each of size n over 2. But then we're going to add to that what? Well, we're going to take n over 4 of the set of nodes and fully connect them with another set of n over 4 nodes. N over 4 from one side, n over 4 from the other. We're looking at all combinations of those. So this becomes our recurrence relation. It's a little bit cumbersome to work with this. It has funny constants in it. So what we're going to do is actually think about it in big theta notation. This is just n squared, right? It's really 1/16 n squared, which is big theta of n squared. All right, let's take a look at what happens in this same kind of tree structure as before, where the amount of edges that we add at each of these levels is some big theta of n squared. So at the top level, it's going to be c n squared. The next level down, it's going to be c n over 2 squared, which is n squared over 4, same thing twice, which is c of n squared over 2. Next level down, we square, we get 16, but there are going to be 4 of these now, so it becomes a quarter. In fact, each level down here, we're getting c n squared over 1 over 2 over 4 over 8 over 16, and so on. And we add all these up, we get c n squared times 1 plus a half plus a quarter plus an eighth and so on, which adds up to something on the order of 2. So when all is said and done, we still have big theta of n squared edges total. So this recurrence relation solves to n squared, which is interesting, right? Because we do n squared really at just the first level. All the other levels that we do, the amount of work gets cut in half each time. And so even though there's possibly a large number of levels, it doesn't add up to anything more than another constant times n squared.